Welcome to Lecture 8, Section 1.7, Relations, using the text Elements of Modern Algebra by Gilbert and Gilbert. This is Dr. Gilbert Eyabi. In this section, we are dealing with relations. I'm going to define the concept of relations and then deal with what is known as equivalence relations and equivalence classes. Before I go ahead and give you a rigorous definition of relations, let me just say that in our study of mathematics, we deal with many examples of relations between elements of various sets. For example, in working with integers, we encounter relations such as x is less than y or x is a factor of y. As a matter of fact, even in calculus, one function may be the derivative of another function or the integral of another function. The property that these examples of relations have in common is that there is an association of some sort between two elements of a set, and the ordering of the elements is important. These relations can be defined more formally as follows. Subsection 1.7.1 Definition. A relation or a binary relation on a non-empty set A is a non-empty set R of ordered pairs x, y such that x is from A and y is from A. Notation-wise, we would say that XRY is read x is related to y, and this notation would mean that x is not related to y. R is the notation we would use to represent a relation. Example: define the relation R on the set of integers by x is related to y if and only if x equals 2y. First question, find 5 elements in R. Remember that elements in R are ordered pairs of the form xy, where x is from A and y is also from A. And in this case, our non-empty set A is the set of integers. So find all pairs xy such that x equals 2y. Solution. The ordered pair 2, 1 is an element in R because I can write 2 as 2 equals 2 times 1, x equals 2y. Same thing for the ordered pair 6, 3. 6 equals 2 times 3, x equals 2y. Is the ordered pair 105, 52 an element in R? If not, then the ordered pair is not an element in R, or we say 105 is not related to 52. Example 2. Define the relation R on the set of integers by x related to y if and only if x squared plus y squared is a multiple of 2, i.e. x squared plus y squared equals 2k, where k is an integer. Find 5 elements in R. I'll leave this second one as a simple exercise for serious students. Subsection 1.7.2 Equivalence relation. A relation R on a non-empty set A is said to be an equivalence relation if the following conditions are satisfied for every x, y, z in A. Number 1, the relation R is reflexive. That means x is related to x for every x in A. Number 2, the relation is symmetric. That means whenever x is related to y, y must also be related to x for every xy in A. 3, R is transitive. That means whenever X is related to Y and Y is related to Z, then X has to be related to Z for every X, Y, Z in A. If these three conditions are satisfied, we say that the given or the defined relation is an equivalence relation. Before we look at an example, let's go ahead and define the concept of congruence modulo n. X is said to be congruent to Y modulo n, denoted by X congruent to Y mod n, if and only if X minus Y equals n times K, where K is an integer. To put that in one simple mathematical sentence, we will say that X is congruent to Y mod n if and only if X minus Y equals nk, where K is an integer. Example, define the relation R on the set of integers by X is related to Y if and only if X is congruent to Y mod 4. I want you to prove that R is an equivalence relation, i.e., reflexivity, symmetry, and transitivity hold. Proof. Very quickly, I want you to recall that X is congruent to Y mod 4 if and only if X minus Y equals 4K, where K is an integer. So let us go ahead and verify reflexivity. Again, I want to prove that X is related to X. Now, for every X in Z, X minus X equals 0, which equals 4 times 0, 4K. So I have written X minus X as 4 times K, where my K is 0 and it is an integer. Whenever X minus Y equals 4K, I would say that X is congruent to Y. So having written X minus X in this form, that means that X is congruent to X mod 4. But by the definition of our relation R, X congruent to Y mod 4 means X is related to Y. So by the definition of our relation R, since X is congruent to X mod 4, I conclude that X is related to X, and therefore our given relation R is reflexive. One down, two to go. 2. Symmetry. For every xy in Z, we suppose that X is related to Y and show that Y is related to X. That is how we prove symmetry. We start first by supposing that X is related to Y, and then we prove that Y is related to X. But X related to Y, what does that mean? X related to Y implies X is congruent to Y mod 4 by our definition of the relation R. Again, by the definition of congruence, that means X minus Y equals 4 times K, where K is an integer. Again, where am I going? I want to prove that Y is related to X. I.e., at the back of my mind, I want to prove that Y minus X equals 4 times some K. But what I have here is X minus Y equals 4K. Multiply this all through by -1, and that gives us Y minus X equals 4 times -K. K is an integer, -1 is an integer, the product of two integers is an integer, so that equals 4 times K wiggle, where my K wiggle is -K, and that is an integer. So I have written Y minus X as 4 times some integer K wiggle, and by the definition of congruence, that means Y is congruent to X mod 4. And by the definition of our relation R, that means Y is related to X. We started with X related to Y, and we just proved that Y is related to X, and that means our relation R is symmetric. 2 down and 1 to go. Transitivity. Suppose X is related to Y and Y is related to Z for every XYZ in Z, where Z is a set of integers. I have to prove that X is related to Z. But X related to Y, what does that mean? X related to Y implies X is congruent to Y mod 4 from the definition of our relation R. From the definition of congruence, X congruent to Y mod 4 implies X minus Y equals 4 times some integer which I would call K1 and call this equation 1. Y related to Z implies that Y is congruent to Z mod 4, and this implies Y minus 4 equals 4K2, where K2 is an integer by the definition of congruence, and we call this equation 2. I want to prove that X is related to Z. In other words, I want to prove that X minus Z equals 4 times some integer K. So I have equations 1 and 2. How would these two equations help me in my quest? Observe that if I add equations 1 and 2, negative y and y would cancel out to give me x minus z, and the right hand side is exactly how I want it to be. So equations 1 and 2 added together would give me x minus z equals 4 into k1 plus k2. K1 is an integer, K2 is an integer. The sum of two integers is an integer, so that equals 4K wiggle, where my K wiggle is K1 plus K2, and that is an element in Z. So I have written X minus Z as 4 times some integer K wiggle. And by the definition of congruence, that means X is congruent to Z mod 4, and that means X is related to Z by the definition of our relation R. And that means R is transitive, and hence we can conclude that our given relation R is an equivalence relation. Reflexivity, symmetry, transitivity, and we conclude R is an equivalence relation. Now that we have stated what it means for a relation R to be an equivalence relation, it is time for us to define the idea of an equivalence class of an element in our non-empty set A. Let R be an equivalence relation on the non-empty set A. Then, for every element A in A, we can define the equivalence class of A to be the set of all elements in A that are related to A. We call that the equivalence class containing the element A. Let's go to an example. Let R be defined on the set of integers Z by X related to Y if and only if X is congruent to Y mod 4. I am using this example again because we just proved that R is an equivalence relation. So I want you to find the equivalence class of 7. Again, by definition, the equivalence class of 7 would be the set of all elements in Z such that the elements are related to 7. I'm going to go through the procedure of finding an equivalence class of an element A in our non-empty set A. Question number 2. I would expect you to be able to find all the distinct equivalence classes for a given equivalence relation R. But before we get to the second question, let us find the equivalence class of 7. By definition, the equivalence class of 7 is a set of all elements X in Z such that X is related to 7. Follow the procedure very carefully. This will be the set of all X in Z such that, what is the definition of our relation R? Such that X is equivalent to 7 mod 4. By the definition of equivalence, this will be the set of all x in Z such that x minus 7 equals 4k, where k is an integer. Do not forget, I am looking for all x in Z that are related to 7. So I solve for x. So this will be the set of all elements x in Z such that x equals 7 plus 4k, where k is an integer. Substitute when k is 0, when k is 1, when k is 2, when k is 3, and so on and so forth. And you would get 7, 11, 15, 19, 23, and it continues in both directions. These are the elements that are related to 7. And this set is the equivalence class containing 7. The second question: how many equivalence classes are there for our relation R as defined? Hint: use this procedure to get the equivalence class of 0, the equivalence class of 1, the equivalence class of 2, the equivalence class of 3, the equivalence class of 4, and observe the sets that you get and come up with a conclusion. I would leave that part as a simple exercise for serious students. Subsection 1.7.4 Partition. If R is an equivalence relation on a non-empty set A, then the distinct equivalence classes of R form a partition of A. That is, each of the equivalence classes is non-empty. Their union would produce the set A, and they are mutually or pairwise disjoint. Let's consider this example. Consider the relation R on Z defined by X related to Y if and only if X is congruent to Y mod 4. Remember this same problem above when I asked you to find all the distinct equivalence classes of the relation R. As a matter of fact, the distinct equivalence classes are 0, 1, 2, and 3. If you're wondering, did we not just find the equivalence class of 7? Well, you realize when you find the equivalence class of 3 that the equivalence class of 3 is actually the same as the equivalence class of 7. And when you find the equivalence class of 4, you realize that it is actually one of these, and then the circle repeats. And the distinct equivalence classes are 0, 1, 2, and 3. So what we are saying is this: the equivalence classes 0, 1, 2, 3 form a partition of the set of integers, i.e., each of these would be non-empty. The union 0, 1, 2, 3 of these equivalence classes would actually give us the set of integers Z, and they are mutually or pairwise disjoint. That means the equivalence class of 0 intersection the equivalence class of 1 is an empty set. The equivalence class of 1 intersection the equivalence class of 2 is an empty set. The equivalence class of 1 intersection the equivalence class of 3 is an empty set, and so on and so forth. Let us go ahead and define partition in general. Let the set A lambda, where lambda is from the indexing set L, be a collection of subsets of the non-empty set A. Then the set of all A lambdas is a partition of A if and only if the following conditions hold. Number 1, each of the A lambdas is non-empty. That means A lambda is not an empty set for every lambda in the indexing set L. Secondly, the union of all the A lambdas equals our non-empty set A. Thirdly, A alpha intersection A beta is an empty set for every alpha different from beta. Alpha and beta are also from our indexing set L. Or we can say that whenever A alpha intersection A beta is different from an empty set, then A alpha must be equal to A beta, or alpha must be equal to beta. This is just the definition of a set being pairwise disjoint or mutually disjoint. So if these three properties are satisfied for every alpha, beta, lambda in our indexing set L, then we conclude that a set of subsets of the non-empty set A would form a partition of A. In closing, let me give you a few problems. Problem number 1. Define the relation R on the set of integers by x is related to y if and only if x is congruent to y mod 7. I want you to use the procedure which we used above to prove that R is an equivalence relation. Once that is completed, I want you to go ahead and find all the distinct equivalence classes of R. Again, start with the equivalence class of 0, the equivalence class of 1, and move up until you find repetition. 3. In general, I want you to prove that if R is an equivalence relation on a non-empty set A, then the distinct equivalence classes of R form a partition of the non-empty set A. Thank you very much. God bless you. Watch out for lecture 9.